Alright, in this video we're actually going to do 4 and 5. 4 and 5, we're going to see our first Rice tables. Rice is reaction, initial, change, equilibrium. It is a way of organizing your data to make it more manageable. Let's go ahead and read the question. We're given the initial partial pressures of PCl5, PCl3, and PCl2 at a temperature. What must occur? What must equilibrium partial pressure be? It gives us Kp also. So that's the pressure at equilibrium. I took about 2 seconds here, let me just before we get into that, and I plugged all these in. I did the products over the reactants and plugged them in just to kind of find out where we are. That's what Q is, right? It's the products, PCl3 times PCl2 divided by PCl5, and right now I've got 0.75. And 0.75 is less than 2.15. So we're not at equilibrium. If Q does not equal K, we're not at equilibrium. If we're not at equilibrium, the reaction has to shift. So, I find these a little bit difficult if you don't really organize the data, so we're going to go through and just like really throw a lot of take all this information out of here, out of up here, and put it into a chart. And it doesn't say you have to do that, but it helps organize you, and it helps you keep everything straight. So, what does it say we have initially? Initially, here we go. We have the PCl5 value, PCl3 value, Cl2 value. Change. This is whether it's going to shift. Is it going to shift to the right or the left? And a lot of times you can apply logic to figure this out. For instance, if this had been 0, it's not. Let's say this was 0. If this value was 0 instead, it would have to shift to the right to add to the 0, because you can't subtract from 0. You'd end up with a negative quantity. But since we do have a value there, we're going to have to give it some more thought. And that thought lies in our analysis of the Q and K that I did earlier. So I have K as 2.15, Q is 0.75, and I like to think of this as 2.15 products for every 1 reactant. More bells. 2.15 products for every 1 reactants, this is the K, versus 0.75 products for every 1 reactant. So do we need to increase or decrease these products? Well, in order to get from here to here, I'd have to have more products. I need to add to the product side to get my Q value to increase until it gets to K. So I need to increase Q. I need to increase the products, and that's why the products have a term being added to it, some unknown quantity. And if I decrease the reactants, that will also help. And this is a sealed system. So since the system is all sealed in the same bottle, all of the products that are made have to come out of the reactants. So as I lose reactants, I'm making that amount of product. For every 1 of these I lose, I'm going to make 1 of these and 1 of those, which kind of makes sense. There's 5 chlorines, and I put 3 of them going to here and 2 of them going to there as they're made. So at equilibrium, I will have this in terms of x, this in terms of x, that in terms of x, and I could throw it all into the equilibrium expression, which I never wrote down. Let's just write that down. K would be equal to PCl3 times Cl2 over PCl5. And then I'm going to take these 3 values for x and put into these 3 spots. And I'm going to use my K. And I have all 4 pieces. 2.15 is K, This is the PCl3, this is this chlorine, this is the PCl5, in terms of an algebraic expression. You have to figure out how you're going to solve that algebraic expression. I prefer to use the solver function in the TI these days. If you do that, just be really careful with your parentheses. There's an entire video already on my YouTube channel on how to use the solver function. You could do the quadratic equation though, that can be cumbersome. You could do check and guess, that works pretty well, where you just plug a value in for x into all three spots and then hit enter and try to make this side eventually equal 2.15. That can take a while though. Anyway, whichever way you solve it, you need to find that as the value for x. It has to be smaller than this term. This is the smallest term up there. Let me just circle that in a different color so it shows up better. This is the smallest value I'm subtracting from. It can't be less than, this value can't be greater than 0.05. If this value was greater than 0.05, you'd end up with a negative quantity of matter, which just is not possible. So after you solve for x, you can plug them in and go, okay, there's minus x, plus x, and these are the true values at equilibrium. This is the molarity of PCl5. This is the molar, oh, it's not molarity. This is the atmospheric pressure from PCl5. This is the atmospheric pressure from PCl3. This is the atmospheric pressure from Cl2. We could even get a total pressure. So how would the system, what would happen to the total pressure of the system as it proceeded towards equilibrium? What would happen to the total pressure of the system as it proceeded to equilibrium? Well, now the total pressure is 0.4768. Did the total pressure increase or decrease? Well, let's just check that. The original total pressure, P total at the beginning was 0.450. Here at the end it's 0.4768. So we should see an increase in pressure. This makes sense to me, and I'll explain why. Why does the pressure increase? Well, if the reaction is shifting from reactants to products, we're gaining products. We went from one particle to two particles. The temperature didn't change. So if we go from one particle to two particles, there's more particles moving around. Shouldn't there be more pressure on the walls of the system? Yeah, the pressure's increasing because there's more particles flying around inside the system. It was before, it was one particle of PCl5. Now it's a particle and another particle. There's two particles being produced for every one, which is why we have more pressure. All right, let's go to number 5. Oh, also, you could take these three values and do a quick check for K. So let's just try that. We have 0.177 times 0.277 divided by 0.0228. Nothing is squared. So I got a quick K value of 2.15, which is the same. So if you take these values and plug them just straight into this, you can check your K and see if the K's match. And then you know if you solve for X correctly, and you get to be very happy that you know you solved it correctly. That can have some variation. A lot of times the last sig fig will be off by 2 or 3 or 4. So if it was off, well, maybe even 6 or 7. If it was off by 7, you might get 2.08. And that would be because the sig figs are rounding here and there, and it just isn't quite adding up. But so if these three values get plugged back in, if you get a rough answer that's close to what it's supposed to be, you can move on with some pretty good confidence. So I would say that these are, if you get values that are that close together, you should be happy with both of them. Number 5 is very similar, except that we're given a mass. And masses are useless, so we should probably change that mass into moles. See, 14 plus 16. So 30.01 grams of NO for every 1 mole. And what's the volume? Volume's 3 liters. So divide all that by 3 liters so that I would have moles divided by volume. And that's where this number comes from. This initial value here for NO is the mass converted to moles, and then the moles divided by the volume to get the molarity. Why are these 0? Let's read the question. Has a K value of 2,400 at 2,000 kelvins. If 0.61 grams are put into a previously empty vessel. Oh, so nitrogen monoxide was put into an empty vessel, so there is none of the products. So that's why. Change. Well, we have to be losing reactants. We have to be making products. We can't lose what we don't have. So we have to be losing on the reactant side here. We're losing 2x worth because we did lose 2 of these for every 1 of each of these we made. So we have, pretty quickly, we can hop into our x expression in terms of equilibrium, and then use whatever function you're going to use to solve it. And that step there's a missing 2 minutes in here, where as you go from here to here, that's going to take time. But so anyway, there's the answer. I only did 2 sig figs because this had 2 and that had 2 sig figs, and I just dropped the rest. When you plug it back in, it almost destroys the NO, and then you have, these guys are both x, and this is an example where if you plug those values in and try to solve for x, you're not going to get, so I'm using N2 times O2 divided by NO squared, and you end up getting 1,089. You're not really getting close enough, and that's because you're losing sig figs as you do the math. It gets a little ugly there at the end when you have the subtraction, and let's see, minus 2x. Yeah, it gets pretty ugly. So anyway, this is a large K value. Like that's a large K value. You're not going to have any good sig figs. What I mean is this is only 1 sig fig. So this K value I just calculated by doing these 2 divided by that only has 1 sig fig. There it is. 1 sig fig could be off by plus or minus 1. Well, if you do plus 1, it's 2,000. So it is within the realm of sig figs. It's just not a pretty check. It doesn't always hit perfectly. If you have fewer sig figs, the less likely K is to actually connect when you go back to do the check method. Alright, so there's 4 and 5. Pause for the next video.